This is part 4 of Chapter 1 lecture. We are going to talk about dimensional analysis, precision, and talk about the question of zeros, significant digits, and then how to do a few conversions and a few calculation problems. Dimensional analysis is a technique, a method that we use to convert from one physical quantity expressed in a particular way, to the same quantity but expressed in a different way. So if we have physical quantities that are expressed in terms of the same fundamental quantities, such as mass or length or time, those same quantities that we mentioned earlier in the SI system, they can be related to each other, and then we can use them to calculate the same quantity but express it in a different way. For example, what do we mean by that? If I have a unit of length here, which is a fundamental quantity, and if I want to express it, to take it from meter, which is expressed in a particular term, in a particular unit, and I want to convert it to a different unit, but it's still length. Okay, I have a fundamental quantity, but it's just expressed in a slightly different way. And I can do this because I know the relationship between a meter and a centimeter, and therefore I can take 10 meters and I can convert it to centimeters by doing what we call dimensional analysis. And we will do a bunch of these problems. But know that this is just a method that we use to take a fundamental quality such as a mass or a length that is expressed in one unit, and then we can convert it, knowing what the relationships are between different units. We can convert it to something else completely. We can also we've been talking about the metric system, but we can take the metric system and we can convert it to the English system. And we can also convert from units in the English system to other units in the English system. These are for length, for example, and these are volume, mass, etc., etc. So we know the relationship between meters and feet. 1 meter is equal to 3.3 feet. So we can use that relationship to convert from this unit of length, the metric system, to something equivalent but in the completely different system. It's in the English system. So we use what we call conversion factors. These are fractions that we can use to show the relationship between those two units. We can write them as 3.3 feet over 1 meter, or put the meter on top and the 3.3 feet at the bottom in this case, depending on which direction I'm going, whether I'm going from meters to feet or feet to meters. I will use one of these conversion factors. And the way that I use that, or the method that I use, is called dimensional analysis. Just a fancy name for doing a little bit of math. What I've done for all of these, for all of the problems that are mentioned in this chapter, I have worked them out specifically. I've made different videos, and then I have linked the videos to these. As you read or go through the PowerPoint slides, you can click on the video and it will take you directly to YouTube, and you can watch how to actually do this particular problem. So I'm not going to spend time talking you through how to work these problems because I've already done them in videos. Now, when we take a measurement, we hardly ever take exact measurements of exact divisions, and therefore there's a little bit of an uncertainty that comes from doing any measurement. And anytime you take a measurement, you have a degree of uncertainty, and those are signified by using significant figures. So what do I mean by a measurement uncertainty? If I make a measurement, I can only be as precise or as my least precise measurement. I cannot go further than that because that limits me. Let's talk about precision in a measurement by looking at trying to figure out the height of this particular column here. Okay, so if I have this axis over here and I have it divided into equal parts, and let's say each one of these represent a centimeter. If I'm looking at the length or the height of this column, as it is right now, divided into 4 parts, all I can say is that this column is at least 3, but it's not quite at 4 yet. So what I know for sure is that it is at 3. But the other digit I don't know for sure. I can say that, well, it's a little over 5, so I can estimate this to be about 3.7, but that 7, the 0.7, that digit is not really precise because I'm guessing. And that is what limits my precision is how accurate can I get to, or how many divisions of the scale I can get. For this one, because I only have it divided into 4 parts, I'm not very precise in my measurement. I can say for certain that it is 3, but I don't know that next digit, and so I'm limited by how many divisions I have in this scale. Now what if I divided my units here, which are 1 really, I divided them in 2. So now my division is half. My steps, if you will, are half. So half, 1, 1.5, 2, 2.5, 3, 3.54. Okay, now I can say for certain that my height is at least 3.5. So I gained 1 more digit in my precision here. But I'm uncertain as to what comes next. It's not quite another 0.5 or a half of my 0.5, so I can say it's about, well, 3.54. I'm guessing at that particular digit, but I have 2 digits that I'm really certain of. I am certain of the 3 and I'm certain of the 0.5 because I have added another division here in my measurement, and therefore I can make a measurement that is better than my first one because now I am sure of 2 digits versus 1 digit that I was when I just had divisions of 1. Now I have divisions of half, so I have 2 digits that I am very sure of. What would happen if I divided it into another half? So I took the halves and I divided them into halves, which means that I've divided into fourths. My original 1 division is divided into fourths. So now I have 0.25, 0.5, 0.75, 1, 1.25, 1.5, 1.75, and 2, etc., etc. Well, this is not quite exactly at 3.75, so I can still estimate it's between 3.5 and 3.75, but it's closer to 3.75, so I can say with a little bit more precision that this is probably about 3.5, about 3.7. Now if I continued to divide all of my divisions into halves, I could really get very close to the height of this column. So you can see that the more divisions you have, the more precise your scale is, the better your precision is going to be of the measurement that you're doing. So therefore, if I have let's say a graduated cylinder that it's a 1 liter graduated cylinder and it has divisions of 50, and a graduated cylinder that is a 10 milliliter and it has a division of zero point 0.1 milliliters, I would say that my most precise instrument would be the 10 milliliter versus the 1 liter because my divisions are smaller. So when my divisions here were 1, so 1, 1, 1, my precision wasn't very good. But then when I divided them a lot more, so into fourths, my precision got better. So the smaller the divisions of your scale, of your instrument, the better your measurement is going to be, the more precise it's going to be. But there's always going to be a little bit of uncertainty, and that is determined by the very last digit. That very last digit is going to be the one that you guess on, and that is going to be the least precise out of all of the other digits. So when I say that the height of this column is 3.7, I know that the 7 is my least precise digit. Now we talk about two different things when we talk about a measurement: accuracy and precision. There's a difference between these two. So accuracy, we talk about accuracy when we talk about how close my measurement that I make with an instrument is to the true value. So how close do I get? There's always a little bit of uncertainty associated, but how close do I get when I make a measurement to the true value? And when I'm measuring, let's say 1 milliliter in a 10 milliliter cylinder versus the 1 liter cylinder, the 10 milliliter is a better instrument to measure that small of an amount than 1 liter. That's because my divisions are better and I have a more precise instrument. Precision, on the other hand, is related to the measuring, so whatever your measuring tool is or your instrument, and it has to do with the size of the increments or the divisions. Just like we said here, when you have a division of 1, it's not as precise as if you have a division of 0.5 or 0.25. So the more divisions you have, the smaller the increments, the better that your precision is going to be. Obviously, here it is: the smaller the increment, the more precise the instrument, and the more precise your measurement is going to be. We then use significant figures to express the precision of an instrument, which is used to make the measurement. The better the precision of the instrument, the more significant digits you're going to have listed. And therefore, this becomes important when we make measurements. Here's kind of a pictorial that will show you accuracy and precision. If you're looking at this scenario, number 1 over here, if this is my bullseye and this is the true value, and I get this grouping, this means that I'm actually very accurate because I am hitting the bullseye most of the time, very, very close to the true value. And I'm also precise because all of my measurements are very close to each other, which means that the instrument that I'm using is very precise. It gives me repeatedly very readings that are very close to each other. Now let's look at this scenario over here. If I have this scenario, look at my grouping, which means that all of these measurements that I'm taking are very close to each other, which means I have a precise tool. However, I'm not very accurate because I am very far from my true value over here. So in this scenario, I am precise, but I'm not very accurate. And then my last one, this one over here, well, I'm neither accurate nor precise because look at how far away all of my measurements are from each other, which means that my precision is very low, and I am nowhere near my true value, which means that I'm not very accurate either. What we want to do with our measurements is this: we want to be accurate, as close to the true value as possible, and we also want an instrument that will be very precise, that will give us repeatedly answers that are very close to each other, or measurements that are very close to each other. That is our goal as scientists. Now, we may be here, and that could be we could be inaccurate due to human error. If my instrument is precise and I'm not accurate, that means that it's probably due to human error. If I get values that agree with each other, they're very close. So if I repeat the same measurement several times and I get very close answers, but they're not so I'm precise, but I'm not accurate because I'm not close to the true value, that means that I am probably making a human error instead of an instrument error. If I'm all over the place, then it's kind of both. So let's talk about the significant digits, but before we do that, we have to kind of address the question of zeros. And this is very important. We need to know what digits are significant and what digits are not significant. And the most confusing one for students are the question of zeros. When do I count zeros and when do I not? So this is the rules that we're going to follow for zeros. Zeros that denote magnitude, that are there just for place value, holding a place, are not significant. Zeros that are part of the measurement, they are significant. So anytime zeros appear after a decimal place, or if you have a decimal place right after the digit, that means that those zeros are significant. What do I mean? So let's talk about this one, for example. This zero here is significant because it's trapped between two non-zero digits. Every non-zero digit is significant, and if you have a zero in between non-zero digits, that zero becomes significant. So we know that this one is significant. Let's look at this one. This one is a zero that is part of my measurement. It's a zero that comes right after my decimal point, which means that it is significant. Therefore, both of these zeros are significant, and this number has 5 significant digits. All of these digits are significant. I cannot drop any of them. Let's look at this example over here. I have 0.00456. Well, these 3 digits over here are non-zero digits, so they're all significant. These zeros over here are called leading zeros. They are not significant. They just hold a place there. I could take this number and I could write it as 4.56 times 10 to the minus 3, which means that I get rid of these zeros and I have only 3 digits that are significant. So this number has only 3 significant digits. These zeros then I can get rid of because they're called leading zeros. Let's look at this one. If you have this number, 52 million, and as you can see, I have no decimal point right here, then these zeros are not considered significant. This number as it is written has only 2 significant digits because it has only those 2 non-zero digits. All the zeros I can get rid of by writing 5.2 times 10 to the 1, 2, 3, 4, 5, 6, 7. So 5.2 times 10 to the 7th. That means I can get rid of all of those zeros without changing anything. I only have 2 significant digits. Now, if I were to place a decimal point right here, that would make all of these zeros significant. So if you have a decimal place after the 0 or even before the 0, that means that those zeros become significant. So in this case, if I put a decimal place right here, that means that all of these zeros now are significant, and this number would have 8 significant digits. So 2 and 6, 8 digits. But if I don't have, the way it's written, I don't have a decimal there, a decimal point, which means that the zeros are just placeholders and they're not significant. I only have 2 significant digits. Okay, I have these problems, let's look at these. We have 345.00. From this example over here, we know that if we have this decimal point and then we followed by zeros, those zeros will be significant. Therefore, this number will have 1, 2, 3, 4, 5 significant digits. Let's look at this number. These zeros here are trapped between non-zero numbers, therefore they are significant. But these zeros are not, they're leading zeros. I can write this number as 3.0045 times 10 to the minus 3, which means that these zeros are not significant, but these are. Therefore, this number has 1, 2, 3, 4, 5 significant digits as well. Now let's look at this number here. All of these zeros are trapped between non-zero digits, and therefore they're all significant. This number has 1, 2, 3, 4, 5, 6, 7 significant digits. And then here's this number written in scientific notation. I have only 2 significant digits here. If I were to write all those zeros out, they would not be significant. Therefore, I only have 2 significant digits here. I have a bunch of examples that I have made videos for you, so they will be in a couple more slides, but watch those problems and you can figure out how to deal with significant digits. Now let's talk about rules when we have operations to do. So when we have addition or subtraction or multiplication and division between numbers, how do we deal with significant digits in those cases? Well, this is always the answer, okay? The rule is that my answer must have the same number of significant digits as the least precise value in the equation, whether I'm adding or subtracting or multiplying or dividing. The trouble is when we look at addition and subtraction or multiplication division, how we determine that least precise value is slightly different. So you need to memorize these rules. When we add or subtract, my answer has to have the same number of digits after my decimal place as the number that has the least digits out of all the numbers that I add or subtract. This is the rule for addition and subtraction. So if I'm adding or subtracting two numbers, my answer cannot have any more digits after my decimal place as the one number that I'm adding or subtracting that has the least amount. So let's say if I have 3.7 plus 3.75, my answer cannot have any more digits after the decimal place as 3.7 does. 3.7 has 1, 3.75 has 2, so my answer cannot have 2 digits after my decimal point. It can only have 1. And I have a bunch of examples in the next few slides that will illustrate this. Multiplying and dividing, the rule is slightly different. My answer has to have the same number of significant digits as the number that has the least amount of significant digits out of all the numbers that are multiplied or divided. So this is when we multiply or divide, we look at the total number of significant digits out of all the numbers. When we add or subtract, we look at the numbers of decimal, so the numbers after the decimal point. I have these examples here and I have worked them out so you can watch them you can watch the video on YouTube on how to do these. But I have subtraction and addition here and multiplication and division here. So when I add these numbers, my answer cannot have any more digits after the decimal place as the one that has the least. 9 here has no digits after the decimal point. It doesn't even have a decimal point. This has 1 and this has 2, which means that my answer will not have any digits after decimal place because 9 will be my limiting factor. Here, this has 2, this has 1, this has 3, which means my answer will only have one digit after my decimal point because 12.1 will limit it, etc., etc. And here, I look at the total number of significant digits. This number has 2 and this number has 3, which means that my answer will only have 2 significant digits because I'm multiplying. Watch the video and follow along. I have them over here as well. I have the answers, but if you want to see the full answers and how they're worked out, just click on the video. There's more examples over here, and you can, the first part goes through A through F, and the second link takes you through G through L. These are some, you have a few that are mixed. For example, here you have a subtraction and a division. So how do you deal with rules? Here you have division and multiplication, etc., etc. So watch these videos, and if you have any questions, please ask. I also have some conversion problems. These are the last 2 slides, and I want you to follow along as I do these problems on the video, but I want you to follow along and figure out how to use dimensional analysis and how to work through systematically each of these problems. For this one, and this is the last slide from chapter 1, I also have worked these problems out. So click on these and watch the videos. And if you have any questions on how to do the problems, you can ask me and I will be more than happy to help you. This concludes the lecture for chapter 1.